fellows, and that joy falls to Dimitri and Ville. Apologies for the pronunciation. Patrick keeps telling me I need to learn to speak English. Dimitri completed his Masters and PhD in his native Belgium in Ghent, 2002, before he crossed the border into Switzerland to work first in EPFL and then to University of Geneva. And he's currently in a position in EPFL with an affiliation with the University of Geneva. And Dimitri is particularly interested in imaging, but imaging, non-invasive imaging of the brain to help us understand how the human body functions, an area that's a very rich topic for signal and image processing to be explored. So without further ado, if I could ask Dimitri to come up and to deliver his plenary, which I'm sure will be wonderful. Dimitri.
Okay, great. So it's a little break to check your emails. So thank you very much for this honor to be displayed to you today. So I will talk about signals, graphs, and brains. And as you will see, this is a rather interdisciplinary thing. So to start with a little bit of history, there has been a quest for brain mapping for at least 1,000 years. So if we go back to Persia, Ibn Sina, or known as Avicenna in the West, was already thinking about assigning specific function to special brain regions. Like, let's say, a brain region to process visual, auditory, and other types of stimuli. And when he wrote his Canon of Medicine, more than 1,000 years ago, he was already speculating on that, and you can see that in this illustration, that he assigned in these bubbles different functions. And actually, about 200 years ago, Franz Joseph Gall, one of the founders of the so-called phrenology, now known as a pseudoscience, was actually attributing also specific function to specific brain regions and believing that the shape of your skull, the bumps of your skull, would reflect the size of those underlying specialized brain regions. And they even had journals, conferences, and a device called the psychograph that would measure that and give you a report about your personality. And of course, we know that isn't true today, but actually the concept is still living with us. And using modern neuroimaging, we now know for sure that we do have specialized brain regions for certain functions, while at the same time we also know that none of these brain regions actually can do what it does without all the others. So it's at the same time a specialized and a distributed system. Now my imaging modality of choice today will be magnetic resonance imaging. And if you think about this, it's really a marvelous technique that allows us, using nuclear magnetic spins, which in essence is a quantum effect, to accumulate basically those quantum effects into macroscopic images. And to make this happen, well, you need many Nobel Prizes. As you see, not less than 8 Nobel Prizes can be linked to NMR and MRI. And they have been driving and helpful for scientific and technological breakthroughs. Now, today these devices have been installed in research and clinical environments, and they allow us to do non-invasive imaging of the human body and the brain, both in terms of anatomy and function, using essentially an endogenous contrast. So no need to inject a special contrast agent or tracer. You can do whole brain coverage, if you're thinking about neuroimaging, and today you can go down to submillimetric spatial resolution, which is quite an endeavor if you think about it. Now there is a key role for signal processing, and I don't need to tell you that in terms of image acquisition and reconstruction, there is a lot that has been done and that's still going on. Just to name a few topics, there is parallel MR imaging, where you can go for joint reconstructions, for multiple receiving coils. Probably those in the field know about SENS and GRAPPA. There is K-space, or if you want Fourier intersampling, combination of multiple slices, etc. There is a place, of course, for compressed sensing, and more recently also deep learning. But the type of application of signal processing I'm more focusing on is the neuroimaging side of it, which is a little bit more downstream. It's more in the processing of the data, of the functional magnetic resonance data. And to give you a number of examples over the last 2 decades, there have been many extensions to general linear model and statistical analysis. Independent component analysis found specific place in this field. There is, of course, a lot about deconvolution and how to regularize it. And last but not least, there is a lot about brain networks and how you can propose new ways to get insights into how the brain is organized as a network. And that's, of course, the topic of today's talk. So, how can we build a graph for the brain using MRI type of data? Now, there are basically two ways to do so. Let's start off with what I call an atlas of the brain, which is typically given by you. It can be constructed on different grounds, but it's a porcellation of the brain consisting of 100 to 1,000 brain regions, depending on the resolution you like to go for. And then, given that atlas, you can, for instance, take diffusion-weighted MRI data, which is illustrated in the background in the middle there, which can be subjected to tractography, basically revealing you axonal bundles in the white matter. And you can then count how many of those tracks or streamlines, if they're virtual, connect each region to every other region. And if you do that for all pairwise regions, you can come up with a weighted adjacency matrix, if you want, which we refer to as the structural connectome or the wiring diagram of the brain. And this is actually a pretty sparse matrix because the brain is by nature economically wired. So this is in logarithmic scale. If you would see this in regular scale, it would actually look as a very sparse matrix. So that's one way to get to a brain graph. The other popular way in the field is to look at functional magnetic resonance imaging, so where you basically have time-dependent data, which is reflecting brain activity. And so now for every of those regions of your atlas, you get a time series, and you will compute all the pairwise correlations between those time series. So if you do that again, you can put that together in a weighted adjacency matrix, which we refer to as the functional connector. And think about this as the communication diagram of the brain. And in that case, we have values, of course, between -1 and +1, because these are correlation coefficients. So those are two popular ways to come up with the brain graph out of two different types of MRI data. Now, to give you a little hint about what has been done for the last 15 years in what we call network neuroscience, is to use those graphs to uncover brain organizational principles. And this can be done at various degrees of complexity. Of course, you can start with very simple graph theoretical measures, such as you could look at the degree of the red node, for instance. It's a degree of 4, and you could look at the degree distribution of your brain graph. Or you could look at clustering coefficients to have something a little bit more characterizing the local topology. But you can also push this further and, for instance, think about what might be a kind of a communication strategy in the brain. Could the functional connector in particular be rather explained from a shortest path, like a routing principle, or from a random walk, which is more diffusion, or maybe something in between, which is a percolation type of strategy. So there are many, let's say, ingenious ways to get from mathematical principles and extrapolate that into neurological organization. And of course, we can also have a very more high-level view, attempting to get an insight into the large-scale organization, which is essentially how does the brain integrate. And then we can think about modularity, like community detection, for instance, or we can look at embeddings, how these communities perhaps evolve over time. And the movie you see at the right-hand side here is actually a two-dimensional visualization of a community detection algorithm, where you can see as a subject is aging from 7 to 25, how these communities become more and more integrated. So the brain is actually, as we age and develop, is going from a local to a much more integrated organization, as you can see very clearly here. Okay, so now that was network neuroscience, and this is mostly done, let's say, in the current brain mapping community, but there is a real opportunity here for graph signal processing. And the novelty GSP brings in is that we combine this weighted graph, the brain graph perspective, with explicitly graph signals. And the typical way is to define a graph signal as a graph signal associated to the nodes. So if we have n nodes, we would have a graph signal that we can represent as a vector of length n. So let me do a little sidestep showing you what type of GSP I like to push forward in this talk. And what I like most in GSP is that you can revisit many of our, let's say, classical conventional reasonings about signal processing, and then think about how we could actually not reinvent, but revisit them in the context of graphs. And I call this slide here when Euler meets Fourier, or basically when graph theory meets harmonic analysis. And one way of doing this is to look at the graph Laplacian, which, as we know, is the degree matrix. So all the degrees on the diagonal, this matrix D here, minus the weighted adjacency matrix, which, as many of you know, is basically a way of defining a second-order derivative on the graph. And now, if you look at the eigendecomposition of the graph Laplacian, you can consider this as a way to define a graph Fourier basis. So you can basically think about the eigenvalues as the graph frequency and the eigenvectors as the graph Fourier, as the associated graph Fourier vectors. And this does actually work very well if your graphs are regular enough, which luckily for us is the case for brain graphs. And I'll convince you about that in a second. And so this is truly defining a basis that you can use to project graph signals, as we will see further on. And if this is the first time you see this, just a little sanity check. If I look at a cycle graph, which is essentially a model for a one-dimensional signal with periodic boundary conditions, so you see here the binary adjacency matrix. I construct the Laplacian, so I have a +2 on the diagonal and then -2 on the adjacent connections. And if I look at the eigendecomposition, what you see is indeed that the eigenvalues, they nicely increase with a single zero eigenvalue that is actually associated at the right-hand side with a constant eigenvector, so this is the DC component. And then you see that all the next eigenvalues, they come in pairs. And if you look closely at the eigenvectors, they actually look at 90 degrees phase-shifted versions of one another, which is essentially really like a sine and a cosine. So what we obtain using this general recipe is essentially mathematically equivalent to a discrete Fourier transform, which is, of course, reassuring, given that we want to interpret this as a Fourier transform in the general case. So how does this look like for our brain graphs? So I took the brain graph constructed using diffusion weighted MRI, so it's a structural connectome that I will further on consider as the graph, the one that is rooted into the white matter of our brain. And so if you look at these eigenvectors of the graph Laplacian, indeed they look actually very nice. The first one is the DC, of course, no surprise. The second one, right-hand side, is showing us a contrast between left and right hemisphere. So it's kind of capturing a basic property of the geometry of the brain, which is that we have two hemispheres. Right? And so this comes up completely, let's say, in a data-driven way in a circuit. If you look at the next one, the one over there, this is a contrast anterior-posterior part of the brain, which again actually makes a lot of sense that this would be a major axis of variation encoded into the structural content. And then if we go on, we get more and more complex patterns of interactions, if you want, between different brain regions, and they become more and more specific, though still distributed until the very last eigenvectors. And you also see the eigenvalue spectrum at the left-hand side, which is also indicative of actually a regular graph, because there is no significant eigengap you can notice. Okay, so that's our brain graph and our graph Fourier transform associated with it. Now, what will be our brain graph signals? So we will go back to our fMRI, and I show you here a movie of a typical resting state fMRI acquisition. The movie is actually a little bit accelerated because it would be slower. In reality, it's about 4 times accelerated. And this is resting state, so it means the subject is doing nothing, but as you can see, the brain is still very active, luckily, as a sign for the subject to be alive. And so what we do, as said before, we will still use this atlas to extract from every brain region time series, but now we won't compute these pairwise correlation coefficients, but we will actually just keep the signal as it is. And that's a major difference with what is typically done in network neuroscience, as I told you before. So we basically use a graph signal that becomes time-dependent, and if you stack them all together in a data matrix like here, a graph signal would be a column. Right? So it's a time-dependent graph signal that we consider. And we won't compress it into a functional connector anymore. Okay. But instead, we can now process these graph signals using the tools that we just defined. And if I actually project all those graph signals onto the Fourier vectors of my structural connector, and I look at the energy, and I plot that to you in a log as a function of the eigenvalue versus the energy of the graph Fourier coefficient, what you see here at the right-hand side is the power spectrum, I mean the energy spectral density, and you can see indeed that the low frequency graph Fourier vectors, they load with the highest energy. Okay, so there is clearly, I wouldn't oversell this, I'm not saying it's a power law, but it's a power law trend, which is essentially showing that brain activity is mostly expressed on these very smooth, low-frequency eigenvectors. And that doesn't come for free in a way. I mean, it really tells us something that brain activity is respecting the underlying structure from the anatomy. Which makes sense, but it's something that actually wasn't explicitly shown before. And we're going to exploit that later. But again, a little sidestep into GSP theory, because having a graph Fourier transform is nice, if we like to do something further with it, especially we like to use it to do some nice filter. And we're going to define or to consider graph filters that are shift invariant under the graph rotation. So what that means is that it should commute with the graph rotation, and that automatically means that we should be able to write our graph filters as a polynomial of the graph rotation as it is written here. Now we could stop there, and it is actually a very useful definition of a category of graph filters. But if I bring in my graph Fourier transform, and I basically take my graph signal x, vector x, I transform it into the graph Fourier domain. And now I see what this does on the operation of applying such a graph filter of the category I just mentioned. Then actually you can vectorize things, as you see here at the top. And in essence, this equivalent shift variant convolution that we first started with now turns into a coefficient-wise multiplication. So in other words, if you are in this category of graph filters, you have the equivalent of the Fourier convolution theorem. Okay, except that in the original domain, it is a shift variant convolution, which turns into a multiplication into the graph Fourier. And so this is a particularly useful property, not only to implement the graph filter, but also to design the graph filters. Because now you can design your graph filters by specifying a spectral window, which will actually turn out to be a non-trivial operation in the original graph domain. Because that's one of the major difficulties if you want to have basically the equivalent of a filter mask, because your topology is locally changing, how do you adapt that filter mask? And here you actually have a recipe by doing a detour into the spectral domain. So we apply this recipe to our brain signals, and we're going to start with very simple filters, and there are many ways you could make this more complex. But given this observation that we have all this low energy, low frequency energy in functional signals, we're going to define a low pass, an ideal low pass spectral window that captures that we will interpret as a filter that basically captures brain activity that is aligned with structure, given that power law property. So you see that in the blue, and then we have a complementary ideal high-pass filter, which is supposed to capture activity that is more liberal with respect to brain activity, because there is not much energy in general. And the cutoff, we chose it such that on average across multiple subjects, we have a 50% split. It looks more shifted to the right because that's we have a log scale over here. So actually, to give you some numbers, here we had an atlas of 360 regions, and to get 50% on average of the energy, you need the first 30 eigenvalue. And so the high pass captures is capturing the next 320. So that's about the ratio we're talking about. Okay, so we have this definition of filters. If we apply this now to our time-dependent graph signals, we can get our aligned and our liberal version of the brain activity. And then what we do next is we do this across a whole session of resting state, which is lasting about 10 minutes, and where we have a graph signal every second. And then we want to see how the energy of aligned and liberal is distributed across the brain, across these different nodes. Because if you go with a kind of a spatial stationary hypothesis, you would expect that they're all about equal, right? I mean, there should be no differences. But perhaps we do see significant differences in nodes that capture more or less aligned and liberal energy. And so what we do for that is, after having filtered all these time-dependent graph signals, we compute the energy again of the filtered versions per node. And we construct this ratio of liberal on top of aligned energy that we call the structural decoupling index. So the higher this ratio above 1, the more a node would capture liberal energy. So the more, in our terminology, we would say it is reflecting decoupled activity, decoupled from the underlying energy. And if you construct that map of the structural decoupling index, you get a map you see here at the bottom of the slide, which to a neuroscientist is very characteristic. So just to tell you, this is the back of the brain, this is the front. This is the visual system. This is the occipital lobe. This is very specifically focused on the visual system. Here we are pre- and post-central. This is somatomotor. Here we are on the temporal lobe, superior temporal lobe, and this is the auditory system. So very clearly we have strikingly blue dots, which means very coupled in the sensory regions. So activity in the sensory regions is closely bound to underlying structure. And if you look at where it starts to be less coupled, well, this happens in the parietal lobe and in the frontal lobe, which to no surprise are actually associated to more high-level processes. Okay, so we looked a little bit closer into this, and if you use that map as a gradient to define a gradient in the brain, where you sort rank regions from being the most coupled to the most decoupled, And you actually compare that with EUSIPCO, which is a meta-analytic database of thousands of fMRI papers deriving function from activity in specific regions. You actually get this matrix at the right-hand side, where you can see that regions that are mostly coupled, here in blue, are actually associated to what I would refer to as low-level processes. You see those coupled regions, they refer indeed to visual perception, multisensory processing, reading, motor, eye movements. So concepts which are clearly more low-level, even if they are in reality still very complex. And as we go towards more decoupled regions, we indeed get to concepts that are much more complicated. We get to emotion, to reward-based decision, to social cognition, memory, etc. Okay, so there is indeed this behaviorally relevant gradient as well. And if you then look more carefully in the literature, you see that the so-called sensory motor to association axis is all over the place. And other people have revealed a very similar gradient in the brain using different pieces of evidence. For instance, there is a quite influential paper defining functional gradients. So starting off from this functional connectome that I mentioned before, which has a major functional gradient that actually looks very closely to what we get. It may be even more interesting, there is work on neurodevelopmental axis, again showing that you have neurodevelopmentally a trajectory that goes from the sensory to these high-level regions, which makes sense, but you see the gradient is very, very similar. There is other work on gene expression, where neurons that are faster, they express specific genes, and those like the sensory regions, and neurons that are slower, they tend to be in the more high-level regions, etc. And there's also been links to cognitive flexibility. So you see that using GSP, and let's say starting off with very fundamental principles from signal processing, we can also reveal organization, functional organization of the brain. But maybe what is the novelty here is by combining information from the brain graph, so the structure, with fMRI, so with activity that we consider as signals themselves. So very important here is to give some statistical meaning to these maps. And to do so, we devised a non-parametric method that I'm going to try to explain here, which is starting off from this link between the Laplacian and the smoothness. So as you might know, if you have a certain graph signal here at the right-hand side, you can define the Laplacian smoothness of that signal by looking at the quadratic form. And again, if you take that quadratic form into the graph Fourier domain, you basically see that this becomes a weighted sum of the energy of the graph Fourier coefficients. And obviously, if you would plug in a graph Fourier eigenvector into this equation, you just get a single eigenvalue as its smoothness. So the eigenvalues are reflecting their own smoothness, if you think about it. So using this observation, we said, okay, can we now devise a new framework for non-parametric testing for graph signals? And if you look into the essential idea of non-parametric testing, it's all about devising a proper randomization scheme that maintains still specific features and actually leads you to a strong way of building data under the null hypothesis. So what we thought is, given our empirical graph signals, can we derive surrogate graph signals that have the same smoothness as the empirical ones? And it's actually very easy to do so in the graph Fourier domain, because you can take your graph signal, convert it into the graph Fourier domain, and just randomize the sides of the graph Fourier coefficients. And this is actually reminiscent to what many of you might know as the Fourier phase randomization algorithm using the discrete Fourier transform for time series, except we don't have a complex value in our construction, but we can still randomize the sign. And if you do randomize the sign, it's really a one-liner to see that the smoothness of such surrogate graph signals will be equal to the one of your empirical graph signal. Okay, because obviously in the quadratic form, it doesn't matter if you multiply twice with the same, plus 1 or minus 1. And then the idea is that you can repeat this many, many times, so you generate a distribution of a certain test metric you want to assess under the mode, so for all surrogate graph signals, and then you still have your test metric for the empirical data, and you can look where this empirical value falls within the node distribution. And that gives you a non-parametric way of doing a statistical test, where you actually have maintained the useful property of the data, which in this case is smoothness as seen under the graph equation. And so we did this. So again, this is the map I showed you before. So that's the structural decoupling index you get for the empirical data. And now we have two ways of constructing our surrogate data. Depending on what we consider as the brain graph to generate the surrogate data. And the first thing I will do is I will actually break the structure of the structural connectome to generate the surrogate data. So I replace, to generate the surrogate data, I replace the structural connectome with the so-called configuration model, which, if you like, it's a rank 1 approximation of your weighted adjacency matrix. Okay, so it's the outer multiplication of the degree vector normalized to the total edge weight. So this basically destroys all preferential connectivity, still keeping the degree distribution. And so if you generate those surrogate data like this, and then you measure the structural decoupling index, what you expect would be that everything is very decoupled, right? Because the surrogate data now doesn't see the true brain graph anymore. It still has the same degree distribution, but it's smoothness in a much more generic way, if you want. And indeed, the SDI tells us everything is decoupled. Okay, so this is the first sanity check. Now next, we're going to randomize using the real structure, or the empirical structural connectome. And if we do that, I'll show you again now the SDI under that type of surrogate data. You see that the map is actually not that different from the one we get for the true data. And what this tells us is that there is indeed a lot of information in the structural connectome that reflects in this map of structural decoupling index. Where if you have, let's say, realistic enough functional signals, you will get a very similar map. Yet, if you statistically compare those two maps, you do see that we have significant differences. And what is actually, I think, the most interesting here is that you get much more reddish regions, which mean more decoupled than expected by chance under this non-parametric scheme. And those red regions, they show up especially in parietal and frontal lobe, okay, which tells us that activity in those high-level associative regions is more decoupled than predicted by structure alone. So it means to get that information, you do need a real function, okay, which is very reassuring if you think about it, right? So function has a role to play. Okay, so maybe quickly, I'll speed a little bit up, given the little delay we had in the beginning. So we saw this map with the sensory motor association axis over and over again, and it looked like, you know, there's only this and every subject has the same. And then we thought, if we construct a map actually at an individual level, and even within an individual, we construct a map not only for resting state session, but also for many types of fMRI sessions. And so we took good use of the Human Connectome project, where we have 100 subjects that we selected, and we have, next to resting state, we have 7 other fMRI sessions. And then you can think about two types of games. You can think about so-called fingerprinting, which is trying to identify an individual from his fMRI signature, which in our case will be the structural decoupling index map. Or you can think about task decoding. So can we recognize what the subject is doing from these maps? And if you first go for a simple statistical analysis with two factors, one being the subject, the other one the within subject effect of task, you see here, first of all, the fingerprinting effect. And everything that is more red is more significant. And what you see is that it's mostly the high-level regions that are reddish, which is frontal, parietal, and a lot of cingulate. Okay, and those are known to be very strong association regions. So what makes you unique? The regions I need to use most to identify you as an individual are those. From the other hand, if I want to know what you're doing, I need to focus on the sensory regions. Okay, so you see here again, visual, auditory, and somatomotor. Okay, so the low level is somehow mostly involved into dealing with the task, and the high level is reflecting who you are, independent of what task you're doing. And even if you are, if you really want to do this in a still simple machine learning way, with a relatively easy linear discriminant analysis, you get an almost perfect leave one out cross-validation of 98%, chance level being at 1%, and the task recognition is at about 75, which is a very simple approach. So this can surely be improved if you like. Okay, so how can you push this further? So one of the things you want to get rid of is these atlases, because they have been predefined, and then it's always a discussion, this atlas is maybe better than the other one, it's more coarse, it's more fine, etc. So we thought, can we perhaps push it to the limit and actually forget about the atlas and use the native resolution of our MRI data? Which means, let's construct a graph where a node is a single voxel of the acquisition itself. So this will become a voxel-level brain graph, if you want, where now a single node is a very little cube of about 1 millimeter. And if you do this across both white and gray matter, you get close to 1 million nodes. So you get very large graphs, or relatively large graphs, but they are very sparsely connected because we're only going to encode in terms of connectivity the local connectivity that we can extract from diffusion-weighted MRI. So it's visualized here at the right-hand side, but basically the connections only can run between neighboring voxels. And so, okay, as I said, it's huge but sparse. Still, you can use established numerical eigensolvers, and if you construct a brain graph like this, and you run, you compute the Laplacian and you look at the eigenvectors, they look like this. Okay, now I can directly visualize them like brain volumes. You see again, I have like a DC component, which is actually beautifully showing the major axonal bundles through the white matter. And then I get the second one, which this time is not left-right, but it's anterior-posterior first. And the one afterwards is left-right. But you see the same geometrical structure being captured. And if I go on to the more higher order modes, you see that I have actually one number 4, which is heavily loaded on the cerebellum. It's also very interesting, meaning that this is also a relevant and highly connected region, and so on and so on. Actually, number 6 is also very relevant. It's the major axonal connection between the somatomotor and the deep brain structures, which is actually very relevant for what we do, which is moving around in this world. So you see, you have many of data-driven things that makes total sense in terms of neuroscience. Now, one of the things we can do next is to formulate a graph recovery problem. And so we took our inspiration from a boundary value problem of heat diffusion, where we say, okay, imagine that the heat is the brain activity that we can measure on the gray matter, which is just a part of this very big graph that I constructed. And let's think about something like heat conduction. So activity is going through the white matter, but I cannot measure it. So can I reconstruct a plausible version of this invisible activity in the white matter, given formulating like a graph signal recovery problem? And so what we do is we go with a variation formulation, where we say, okay, we have a data fit on the gray matter. There we should be close to the measured data. And everywhere else, we want to preserve Laplacian smoothness. And if you solve this algorithm, you actually get, as you can see at the right-hand side, you get what I would call an in-painted version of fMRI, which is complementing the activity you can measure with this technique on gray matter with a plausible reconstruction how this activity would look like on the white matter. And to show you that it's relevant for neuroscience, what you see here at the top is the so-called seed connectivity of a region which is the posterior cingulate cortex, which is over here. And this is a map of basically all the correlation of time courses. And so this is the classical map, as everybody knows in brain mapping. If I in-paint my fMRI data and I recompute this map, what you see is that I really get a version now that highlights how this map is supported by the white matter architecture of the brain. And you really see the axonal bundles that actually do connect those gray matter regions that are classically known as being connected, functionally connected to the posterior cingulate cortex. Okay, so a few hints on many other things you could do beyond telepation and maybe, well, I should say beyond transforms you can define based on the location. Something that I always liked were Slepian functions. Actually, you can also bring them closer to graphs. So Euler can also read Slepian, even if it's a bit more distant in time. And so I don't want to spend too much time, of course, here, but you can basically extend the concept of Slepian functions to graphs by thinking again about the band-limited spectral basis, now of course using the graph Fourier transform, that is maximizing energy concentration in a certain subgraph. So subset of nodes. And this can be beautifully solved by optimizing a Rayleigh quotient, where you have the band-limiting matrix and the node selection matrix. And I just have a quick example here on the mesh graph from the leopard, where the subset here is on the head of the animal. And you see that you get actually eigenmodes that are focused on that part, although not strictly limited to. And we can use this for neuroscience in general ways. One way is to look at C. elegans, so this is a little more connectome. And actually the Laplacian embedding of this connectome is a lot used in neuroscience. But now you can have like a Slepian embedding where you focus, for instance, only on the motor neurons. And you see a similar topological organization that you wouldn't be able to review from the global view if you cannot focus. And another example, very quickly, is about replacing the Laplacian maybe with another operator, and there are many. One of them is the modularity matrix. And the modularity matrix plays a crucial role in community structure, which, as many of you have heard, is also a type of organization that occurs in many graphs, including in brain graphs. And in essence, the Laplacian was the degree matrix minus the adjacency matrix. The modularity matrix is the adjacency matrix minus the adjacency matrix of the configuration model, which is that very same model that I used before for my surrogate data, which has no preferential connectivity but still preserves the degree distribution. And then what you could do if you plug in the modularity matrix into the whole scheme I explained to you before, is that instead of doing low pass or high pass filtering, you could actually do now filtering that is promoting in graph signals the modularity, okay, which means interactions within communities. Or you could actually promote anti-modularity, which means parts in the graph signal that are reflecting interactions between communities. And so these are interesting concepts that move us actually beyond what you could take from conventional harmonic analysis within a really much more specific graph setup. Okay, so to conclude, a few challenges and opportunities for the future. And I like to quote here a very recent paper by Ed Wilmore and Alex Forlito, where they say that still one of the most fundamental challenges in neuroimaging is to link macroscopic measures, like the ones I've been using and I've showed you, all those based on MRI, to microscopic cellular processes. And this is a very long endeavor, but we will get there, ultimately, I think. And one way it's moving forward is by using ultra-high field MRI, like 70, where we start to get so-called layer-specific functional signals. And as you can see here at the right side, conceptually you can think about blowing up my node there into something that becomes much more specific inside the node, where I can model now different layers in the gray matter, and I can associate some layers to be processing input and other ones to, sending out output to other nodes. And so that means that I could actually think of going to a directed graph, which has new challenges, new opportunities as well. Another one is to model my nodes within by starting to separate excitatory and inhibitory neural populations, which goes, of course, to dynamic models, but maybe more basically, it goes how to deal properly with signed edge weights. Because now my inhibition will be a kind of a negative input to another region. So again, something that is still state of the art. And then, of course, brain dynamics. How can I start to more properly account for this ongoing brain activity? So treating these time-dependent graph signals more carefully by introducing temporal models. And all this, of course, should be done not only with fMRI, but also with other imaging modalities such as EEG, energy, and probably also invasive measurements if you really want to go down to the microscopic process. And maybe the elephant in the room is machine learning, as already mentioned at the opening. Yes, there are also opportunities for machine learning. Of course, there is a big effort in pushing forward graph neural networks, and I think this is also useful for the field of brain imaging. So you could incorporate prior knowledge, like a brain graph, into a graph neural network, and then to try to use that either to have more insight in, again, organizational principles of the brain, so in a kind of data-driven optimization, and then try to figure out if this makes sense given what we know how the brain works. Or we could also think about it like more a pure machine learning challenge, where perhaps this is a better way of decoding from brain activity. And I like to mention that actually, given the advent now of generative AI, this is starting to pose some emerging legal and ethical issues. So to conclude, so GSP, I think we all agree, it's very versatile. It's a very cool framework to combine graphs and graph signals. And personally, I like most this way of combining it with the principles of harmonic signal analysis, which is a real opportunity for computational neuroimaging and neuroscience. And as I've shown you, it allows you to relate structure and function increasingly at different spatial and temporal scales. So many ways to extend this further: directed and signed graphs, time dependency, and graph neural networks. And if you like to play around with some of the examples I showed you today, we have implementations available on GitHub and the library we're working on. And let me thank the lab for all their contributions. And thank you for your attention. Thank you very much.
Sure,
If there are questions,
happy to take questions.
we have a question there. The microphone is coming.
Yeah, thank you for such a beautiful talk and for such great work. So I have one very basic question which I didn't understand. So a lot of the conclusions that you presented will be affected by the choice, of the points that you place on the graph. So if you change those positions, then certain things may change. So can you throw a little bit of light on how those points were selected and what would happen if there are some minor perturbations in their positions?
So in the first part where I used atlases, so that's where they come from, this choice of defining the nodes. There are many atlases around. And basically the way to prove that your result is robust and makes sense is to validate it with different atlases. And actually the structural decoupling index, it shows up in every atlas. But to go beyond that, the high resolution graph doesn't need to define brain regions in such a, let's say, more macroscopic way. So there is a voxel, and whatever is a brain region might show up as a, let's say, clustered set of voxels / neurons. It is the atlas that plays that role.
Thank you. So I understand mathematically, the analogy with harmonic analysis, the eigenvectors in harmonic analysis are based on a parametric model, which has a frequency, so you can assign frequency. But you also showed a spectrum where low frequencies were on the left and high frequencies on the right. So, but there's no parametric model. So how do you assign these eigenvectors to a position on the spectrum?
Yes, a very good question. So if you go with the, let's say, the first approach, you lose the physical embedding of the graph, right? Because the only thing the graph sees is the connectivity through the white matter by tractography derived from diffusion-weighted MRI. So somehow, I mean, there is no more notion of distance. So I think that answers your question, probably. Now, if we go to the second type of graph, where a node becomes a voxel, actually the physical embedding is reflected in the graph, because the number of hops you do on the graph can be converted in an equivalent physical distance. And there you can actually associate eigenvalues or graph frequencies, if you want, with physical distance again. But with the first approach, you cannot. So that's why the second approach has a promising ingredient as well.
Like a wavelength.
Yes, indeed. And we can actually extract like range maps and things like that.
Thank you, Will. Thank you for this very nice talk. Of course, I'm more involved in EEG, and I just wonder whether the EEG, how you see we also develop graph signal processing in EEG. So how do you make the connection? Because taking EEG and measuring EEG, you can do it more easily than just putting patients and subjects in the scanner. And the second question is, we also have results of using the graphs to go for pathology, to really make a difference and then see pathologic cases, let's say in multiple sclerosis or other diseases.
Yes, thank you. So about EEG and MEG, that has been already done. So people have used a structural graph from the same of type I've been using, but then having the graph signal taken from EEG or MEG. And you get different, though also similar organizational principles that are revealed. So this is something that is ongoing, and maybe one can also think about how can we combine both in the same analysis, like a kind of multi-layer type of approach or similar ideas. For the second question, so from our side, we have already actually applied this to clinical cohorts. We have one work where we looked at 22q11 deletion syndrome. These are individuals with a genetic defect, and they have a very high incidence of schizophrenia. And so they have been followed since early age, and it's basically a longitudinal cohort. And so we show that the structural decoupling index is deviating from the neurotypical pattern that you see in, let's say, normal subjects early on. And it's indicative for whether the subjects unfortunately develop psychosis or not. So it seems to also capture information from a dysfunctional sort.
Yeah, thank you for the talk. And you already mentioned that one of the applications is a clinical application. And what other applications you consider, like thinking of very far? Do you think it will be ever possible to decide if a person has certain abilities in certain fields at some point? Would it be predictable? Would it be a hope?
Mm-hmm. So, I mean, you probably have been triggered by my remark on the ethical issues that are emerging. And I think this is going beyond graph signal processing. I mean, it's true that the combination now of generative AI with neuroimaging modalities in general is somehow unleashing, if you want, mind-reading applications that are beyond imagination before. And so we start to see papers out there that show, it's still at the early side, but still, that show promising results of decoding, for instance, visual images out of visual cortex at a level that is unprecedented. Because you combine it with a lot of prior information from these generative models, and all of a sudden, let's say, the little pieces of information you can get from fMRI and maybe in the future from EEG are enough to give you a good impression about what the person is thinking. And there is a recent paper also about semantic decoding. So not even going back to the sensory level, but what is the semantic process that is going on in somebody's head? And so this is really asking ethical questions, which we should maybe wonder about now before it's too late.
So maybe we come to the end of the questions. Thank you very much for those. And thank you very much to our speaker for this really fascinating